There isn't actually an alert right now. As of the most recent forecast from NOAA's Space Weather Prediction Center, solar activity is sitting at moderate levels, with only a small chance of minor G1 class geomagnetic storming in the coming days, and the broader outlook through the rest of the month expects mostly low activity. Nothing described as Earth's biggest space weather threat is currently building. That framing is exaggerated. That kind of headline follows a familiar pattern. Take a routine forecast update, something that space weather agencies publish essentially every single day as part OF, their normal operations. Strip away the specific numbers and context, and reframe it using the vaguest, most dramatic language possible. Threat is building. Sounds urgent, precisely because it doesn't commit to any actual checkable claim. There's no named storm, no specific date, no measurable intensity attached to it, just an implied sense that something ominous is underway. That's a pattern worth recognizing on its own, separate from whatever the underlying topic happens to be. But underneath that exaggeration is a real, well-documented, and genuinely unsettling story, one that doesn't need any invented urgency to be worth taking seriously. We are living through an active phase of the sun's roughly 11-year cycle, a period when powerful solar storms become more frequent. And scientists have spent decades studying exactly what would happen if Earth took a direct hit from a storm at the extreme end of what the sun is capable of producing. The answer isn't comfortable, and it's not science fiction. It's already happened once in 1859, and every serious space weather scientist studying the problem today agrees it will happen again. The only real questions are when and how ready we'll be. Let's start with what actually happened the one time we got the full, unfiltered version of this event. In early September 1859, astronomer Richard Carrington was observing sunspots through his telescope when he witnessed an intense, sudden brightening on the sun's surface, a solar flare so powerful it remains, to this day, the standard benchmark scientists use for the most extreme space weather event on record. That flare was followed by a coronal mass ejection, an enormous eruption of charged particles and magnetic field hurled outward from the sun, and this particular eruption happened to be aimed almost directly at Earth. It arrived astonishingly fast, with a transit time from flare onset to geomagnetic storm impact of just 17.6 hours, one of the shortest transit times ever recorded, even by modern standards. The effects were extraordinary. Auroras, normally confined to high latitudes near the poles, became visible across nearly the entire planet, with sightings reported as far south as the Caribbean, and in the southern some locations, the night sky glowed brightly enough that people reported being able to read a newspaper by its light. But the more consequential effects showed up in the era's cutting-edge technology: telegraph systems. Wires around the world surged with induced electrical current, shocking operators, setting some telegraph paper on fire, and in a detail that still sounds almost unbelievable today, allowing a handful of telegraph lines to keep transmitting messages even after operators had disconnected their batteries entirely, because the storm itself was generating enough current to power the line. In 1859, that was a remarkable, alarming, but ultimately survivable event, because telegraph systems were a relatively small, replaceable part of how society functioned. The problem is that modern civilization is built entirely differently. We don't just use electricity for a handful of specialized communication lines anymore. We depend on it for essentially everything: our power grids, our water systems, our hospitals, our banking systems, our satellites, our GPS networks, our supply chains. Nearly every piece of modern infrastructure that keeps a technological society running day to day. So what would happen if a storm of that same magnitude or worse hit Earth today? This isn't a hypothetical question scientists are guessing at. It's been the subject of serious, sustained risk analysis for well over a decade, precisely because the stakes are so high. One of the most detailed assessments came from a joint 2013 study conducted by Lloyd's of London, the insurance and risk analysis firm, working alongside the US-based Atmospheric and Environmental Research Group. Their model estimated that a Carrington-level storm striking the modern United States could produce economic damage somewhere between roughly $600 billion and $2.6 trillion, with the higher end of that range tied to a scenario in which the storm's effects concentrate along heavily populated, heavily industrialized regions, including the corridor stretching from Washington, D.C. to New York City, parts of the Midwest, and the Gulf Coast. Under that scenario, the report estimated that somewhere between 20 and 40 million Americans could lose power, with outage durations ranging anywhere from about 16 days on the low end to as long as 1 to 2 years on the high end for the worst affected areas. That enormous range in recovery time comes down to one specific piece of hardware: extra high voltage transformers, the massive custom-built pieces of equipment that form the backbone of long-distance power transmission. These transformers are exactly the part of the grid most vulnerable to the kind of slow-moving, direct current-like electrical surges that geomagnetic storms induce in long transmission lines, called geomagnetically induced currents. In the worst case, some of these transformers could be damaged or destroyed outright. And because they're often custom built to order, sometimes with lead times measured in months or even years, replacing a large number of them all at once could stretch outages out far longer than anyone would expect from an ordinary blackout. We actually have a real modern precedent for exactly this kind of transformer failure, even though it involved a storm far weaker than a full Carrington-level event. In March 1989, a geomagnetic storm swept through the electrical grid operated by Hydro-Quebec in Canada, and within about 90 seconds, it collapsed the entire regional grid, cutting power to roughly 6 million people for approximately 9 hours. That event, sometimes called the Quebec Blackout, remains the most tangible, real-world demonstration of exactly the kind of vulnerability space weather scientists worry about at a much larger scale. There's also a genuinely nerve-wracking near-miss worth knowing about, because it shows this isn't just an old one-time historical event we're extrapolating from. In July 2012, a coronal mass ejection erupted from the Sun with a magnitude scientists believe was comparable to the 1859 Carrington event. It crossed directly through the exact point in Earth's orbit where our planet would have been, had it simply arrived about a week earlier. We were, quite literally, not there yet when it passed through. If Earth's orbital position had lined up differently by only a matter of days, we would likely have experienced a direct hit from a Carrington-class storm in the middle of the 21st century, with our current, heavily electricity-dependent infrastructure directly in its path. Now, it's important to say clearly that not every expert agrees on exactly how catastrophic the worst-case outcome would actually be, and that disagreement itself is part of the honest scientific picture here. One camp of researchers holds the view reflected in the more severe assessments, like the trillion-dollar multi-year recovery scenario, that a Carrington-class storm could knock out a large number of essentially irreplaceable transformers across an entire continent, triggering the kind of prolonged, widespread blackout those worst-case models describe. A more moderate school of thought argues this may overstate the actual risk, suggesting that most transformers would more likely trip offline or suffer damage that's recoverable, rather than being destroyed outright, and that grid operators, once warned of an incoming storm, have real tools available to shed load, and reconfigure their systems to protect the most vulnerable equipment before a storm's peak effects arrive. Both camps, importantly, agree on the core seriously and preparing for. Where they disagree is on the scale of the worst-case outcome, and that disagreement remains genuinely unsettled, in large part because we simply don't have a clean, modern data point to calibrate against. The 2012 near miss came agonizingly close to giving researchers exactly that data point, and instead gave us a warning without the consequences. So what has actually been done in the years since scientists began taking this risk seriously to reduce our exposure? Quite a lot, though experts differ on whether it's been enough. After the 1989 Quebec storm exposed just how vulnerable a modern grid could be, the Canadian government invested roughly 1.2 billion Canadian dollars, specifically hardening the Hydro-Quebec grid against future geomagnetic disturbances. In the United States, federal regulators eventually introduced mandatory reliability standards through the Federal Energy Regulatory Commission, specifically addressing geomagnetic disturbance risk, requiring utility operators to assess and plan for this kind of event. However, some space weather researchers note that actual capital investment in physically hardening the most exposed, highest-risk sections of the American grid has lagged well behind the scale of investment recommended by risk assessments like the Lloyd's report, and behind what Canada undertook after its own direct experience with grid failure in 1989. One of the more affordable protective measures researchers have proposed involves installing devices called blocking capacitors on the grid's most vulnerable extra-high voltage transformers, essentially hardware designed to block the slow, direct current-like surges a geomagnetic storm induces before they can damage the transformer itself. According to the 2013 Lloyd's assessment, outfitting roughly the 1,000 most vulnerable transformers in the United States with this kind of protection would cost in the neighborhood of $100 million, a comparatively modest figure set against the trillions of dollars in potential damage a worst-case storm could cause. Whether that kind of comprehensive hardening effort has actually been carried out at the scale researchers recommended remains an open, actively debated question within the space weather and grid security research communities. Beyond hardening physical infrastructure, the other major line of defense is early warning, and this is where our situation today looks genuinely different from 1859. Modern space agencies operate a network of dedicated instruments specifically built to monitor the sun and track incoming solar eruptions. NASA's Solar Dynamics Observatory continuously images the sun's surface, watching for flares and eruptions as they happen. NOAA's Space Weather Prediction Center models the trajectory and speed of coronal mass ejections as they travel outward from the sun, giving grid operators, satellite, companies, and airlines advance notice, sometimes measured in hours, occasionally in a day or more, before a storm's effects reach Earth. That warning window matters enormously because it's precisely the kind of lead time that allows grid operators to proactively reduce electrical load, reconfigure vulnerable sections of the network, and take other protective steps before a storm's peak. Effects hit exactly the kind of mitigation the more moderate risk assessments are counting on to prevent a worst-case, multi-year blackout scenario from actually playing out. There's a genuine vulnerability hiding inside that early warning system, though, one that doesn't get nearly as much attention as it probably deserves. A significant portion of the satellites currently providing that crucial handful of hours of advance warning are, according to researchers who track this issue, operating well past their originally planned mission lifespans. If those aging monitoring satellites were to fail, whether from ordinary equipment degradation or, with a certain grim irony, from being damaged by a severe solar storm themselves before a replacement network is fully in place, our actual warning time before a major storm's impact could shrink significantly, right at the exact moment we'd need it most. It's worth understanding where we actually stand in the sun's own natural rhythm right now, because that context matters more than any single alarming headline. The sun runs on an activity cycle lasting roughly 11 years, swinging between quiet minimums and much more active maximums, driven by the gradual reversal of its magnetic field. We are currently in the active portion of what scientists call solar cycle 25, and this particular cycle has already produced some genuinely remarkable events, well beyond routine background activity. In May 2024, a cluster of powerful X-class solar flares, combined with multiple coronal mass ejections, launched in quick succession, triggered one of the strongest geomagnetic storms of the entire 21st century so far, reaching G5, the maximum severity level on NOAA's geomagnetic storm scale. That storm produced widespread auroras visible across huge stretches of North America, Europe, and even parts of Australia, in some cases at latitudes that almost never see the northern or southern lights at all. Satellite operators reported temporary communication disruptions and elevated radiation exposure levels during the event. Just months later, in October 2024, a separate fast-moving CME, traveling at speeds of over 1,200 kilometers per second, triggered another severe G4-level storm, one of the most intense geomagnetic disturbances recorded that year. Neither of those 2024 storms, severe as they were, came anywhere close to Carrington-level intensity, and thankfully, neither produced anything resembling the kind of catastrophic, prolonged grid failure that the worst-case risk models describe. According to the European Space Agency, no long-term satellite damage was reported from the May 2024 event, despite its severity. But both storms are useful. Recent reminders that solar cycle 25 is actively capable of producing storms at the higher end of NOAA's severity scale, and that the kind of extreme space weather scientists worry about isn't some distant, purely theoretical concern confined to 19th century history books. It's something the sun has demonstrated it's still fully capable of producing, repeatedly, within just the last couple of years. It's also worth knowing that grid infrastructure isn't the only modern system exposed to this kind of risk, even if it tends to dominate the worst-case damage estimates. GPS and satellite navigation systems can experience degraded accuracy or temporary outages during severe geomagnetic storms, which has real consequences for aviation, shipping, and increasingly for autonomous vehicles and precision agriculture equipment that depend on accurate positioning data. High-frequency radio communication, still relied upon for some aviation and maritime operations, can suffer significant degradation or complete blackouts during major solar radio storms. Airlines have, on occasion, chosen to reroute polar flights specifically to avoid the increased radiation exposure and communication disruption associated with severe geomagnetic activity happening at high latitudes. And satellites themselves, particularly the growing number of low Earth orbit satellites, now used for global intern-T service, face increased atmospheric drag during severe storms, since intense geomagnetic activity heats and expands Earth's upper atmosphere, a real and increasingly relevant concern given how rapidly the number of active satellites in low orbit has grown in recent years. It's worth stepping back and considering why this particular risk tends to get treated so differently from other natural disasters we prepare for regularly, like hurricanes or earthquakes. Part of it is simply timescale. A magnitude 9 earthquake or a major hurricane is something most regions can expect to experience, in some form, within a human lifetime or two, which keeps the risk present in public consciousness and embedded in building codes and emergency planning. A Carrington-class solar storm striking a heavily populated, technological, high-dependent region is a much rarer event on human timescales, even though, on the timescale the Sun actually operates on, scientists consider its eventual recurrence not a matter of if, but simply when. That mismatch between how rare the event feels to any one person and how statistically certain scientists consider its eventual occurrence to be makes it a uniquely difficult risk to keep in the public's attention without either being ignored entirely or, alternatively, getting inflated into exactly the kind of exaggerated ready-made panic that headlines promising an imminent building threat tend to traffic in. The honest, useful version of this story sits somewhere in the middle of those two extremes. It's not an emergency happening right now. Current solar activity, as forecasters have measured it, is unremarkable, sitting at routine, moderate levels with nothing unusual building toward Earth in the immediate future. But it is a real, scientifically well-documented risk that our current infrastructure remains meaningfully exposed to, one that's already produced a direct historical precedent in 1859, a smaller scale real-world demonstration of grid vulnerability in 1989, and a startlingly close near miss in 2012 that easily could have given us a second, far more consequential direct hit on a fully modern, electricity-dependent civilization. Scientists studying this risk aren't asking anyone to panic. What they're generally asking for is sustained, adequately funded investment in the two things that actually make a measurable difference: physically hardening the most vulnerable pieces of grid infrastructure against geomagnetically induced currents, and maintaining, and eventually replacing, the aging fleet of satellites currently providing our only meaningful advance warning before a storm like this arrives. Both of those are solvable engineering and policy problems. Neither of them requires exaggerating today's actual fairly ordinary solar conditions into something they're not. The Sun doesn't need help sounding dramatic. It produced the most extreme space weather event in recorded history using nothing but its own physics over a century and a half ago, and it remains fully capable of doing it again on its own timeline without any headlines' help. The real story here was never about manufacturing urgency out of nothing. It's about taking a genuine, well-understood, statistically inevitable risk seriously enough today, on an ordinary, unremarkable day when nothing in particular is building, to actually be ready the next time the Sun decides to show us exactly what a truly extreme storm looks like. And when that day eventually comes, however far off it turns out to be, it likely won't arrive with the kind of dramatic telegraphed warning a headline like "Earth's biggest space weather threat is building" implies. It will more likely look exactly like most of the genuine warnings space weather forecasters issue today: a routine bulletin, a measured probability, a modest window of advance notice, quietly published on a government website most people never check, describing a storm that, this time, simply turns out to be the real one. The value of taking this risk seriously now isn't about living in a state of constant alarm. It's about making sure that when that ordinary-sounding bulletin eventually turns out to matter more than any of the countless routine ones that came before it, the grid, the satellites, and the systems we all depend on are actually ready to meet it.